All right, everyone. Well, I'm going to go ahead and do a voiceover PowerPoint for this class on October 20th because unfortunately I did not have my microphone working. So the topic was competition and community structure. And so we just talked about predation and mentioned the ways that predation affects prey. It causes prey to use different habitats. It can actually reduce population from direct effects, or it can lead to reduction in growth and fitness, even without direct consumption, right? So the example of the Pekarsky study with the stoneflies, predatory stoneflies with their mouth parts glued. So we're going to continue our discussion of biotic forces and their interactions in streams with competition. So this is an important topic in ecology in general, and so it's good to think about when competition happens. And so in general, it's when resources are in short supply. So some of y'all remember Thomas Malthus's idea about populations being able to increase exponentially, but resources only increasing linearly. And so you get to a point where there are more individuals than the resources can support. And at that time, competition happens. And we can talk about two different types, either exploitation or interference competition. The best way to think about it is interference competition is like what we're seeing in the picture here with these eagles, when individuals physically interfere with another's ability to acquire the resources. They exclude them from the resources. And then there's exploitation competition, where one individual outcompetes another simply by using up the resource faster. And I shared the silly example of pizza parties, where if there are not enough pizzas to go around and some of the people just block everyone out away from the pizzas, then they're practicing interference competition. But then there might be some folks that can just eat the pizza really fast. And so if they just get there and eat the pizza up before others can, that's exploitation competition. Kind of a silly example, I admit. So again, thinking about why competition occurs, some concepts which I know were discussed in 241, right? Gauss's competitive exclusion principle, that no two species can occupy the same niche indefinitely when resources are limiting. So there's a couple qualifiers here. The first is indefinitely, right? So it means that species can occupy the same niche for a short period of time, but not indefinitely. And finally, that they can't do that when resources are limiting. So when there are plenty of resources to go around, species can occupy the same niche. They can also occupy the same niche for a small amount of time, but when resources become limiting, they can't occupy the same niche indefinitely. And there's a few ways we can define an ecological niche. The best way to define it that I know of that helps to sort of unpack the theory, as we say, that is, help us actually develop testable predictions, has to do with this idea of an n-dimensional hypervolume. What does that mean? Well, if we think of the number of resources and conditions that are required for a species to survive, that's going to define its niche. Now, remember, a resource competition can happen over. Conditions competition doesn't happen over, right? So, if one species prefers cold temperatures and one species prefers warm temperatures, they're not going to use up the preferred temperature. However, if one of them prefers a certain size of food, they could very well use up that size of food. So the niche talks about resources and conditions, but for competition's sake, we're really concerned about resources. So you imagine all these different what we call resource axes. So an example with an anole lizard, imagine that this species feeds on a certain range of food size, and that's the one axis up at the top. But then let's imagine that the species not only feeds on that particular food size, but also forages at a certain height of a tree. So this square represents sort of the two-dimensional niche space. Okay, well then we can add on a third axis, say the light levels that the species feeds under. And so now we have kind of a three-dimensional niche space. So as you can imagine, we can add more and more axes to this niche. And it becomes hard to conceptualize at a certain point, but you get the idea, right? As long as all of these axes don't overlap for a species, they're not going to compete. With the anole lizard in this example, you could have another anole that feeds on the same size food, under the same light conditions, but at a different foraging height. And so those two species won't compete because there's not overlap with all niche axes. So how do organisms evolve to minimize competition? Well, this is niche partitioning, or sometimes called resource partitioning. And that is just this idea that species will evolve to minimize overlap in resource use. So we've talked about rivers and streams and how important disturbance is, and abiotic factors play a strong role. But we've been discussing, the fact that biotic interactions can be important in determining community structure and determining what species are able to exist there. So this author looked at filter feeding caddisfly species, where there were several of them that occurred together, and the question was, you wouldn't expect that they could all be feeding in the same way because of the principle of competitive exclusion. So they went in and measured some of these niche axes, if you will. They looked at the depth of the water where they occurred, the current velocity, some food resources, the quantity of mosses, the quantity of CPOM, the volume of the stone where they occurred, and then the Froude number, which is a measure of turbulence in the water. And lo and behold, when you looked at many of these species, what you saw was that they didn't overlap much. You found resources that they partitioned. So for instance, you can see the depth. Some of these species were at about 7 centimeters. Others were deeper, right? And so you can pick really any two pairs, and you can find resources where they don't overlap a lot. So it looks like, it turns out all these are filter feeding caddisflies, but they're each acquiring their resources in a little different way. And so there is evidence for niche partitioning in stream ecology. But the question is that evidence of competition? So we need to know a couple of things. Again, we need to know if resources are limiting, right? Because if resources aren't limiting, well, then competition wouldn't be occurring, right? It wouldn't expect to occur. You'd also need to know if those species evolved together or separately. Because if those species evolved their way of feeding in separate environments and then came together after the fact, then competition wouldn't have played a role. So for instance, there are certain fish species that have been around relatively unchanged for tens of millions of years. They've been around before the streams that we see today existed. And so to look at these species in a stream now and say that they've evolved in response to competition here in this stream wouldn't make sense because their bodies have not changed in the last tens of millions of years. However, if you do have a case now where resources are limiting, then you might expect there to be variation. And we've found evidence for this in different places. So how do you know if resources are limiting? Well, you have to look and see if a reduction in resource abundance affects the species negatively. And again, evolutionarily, negatively means reduced fitness, not having as many babies. So here's an example looking at snails and periphyton in White Oak Creek in Tennessee, a stream that's not unlike the streams in our neck of the woods in the southern Appalachians. So these authors conducted an experiment with 4 different levels of treatment. So they had areas that were shaded and areas that were open in this stream. And of course, you would expect, right, that in the open site, there would be more photosynthesis going on than in the shaded site. Then they manipulated snail density. And so they had normal snail density and low snail density under each of those treatments. And so the idea was, light is a resource for algae, and algae is a resource for snails. And so they monitored rates of photosynthesis, kind of like we did in our study. And then they also looked at the growth rate of these snails, as well as fat content, right? Because organisms store energy in fats. And so that's a way of measuring how much food they're acquiring, how many resources they're acquiring. So thinking about what would happen if resources are limiting, right? You would expect that when there's less sunlight, then the periphyton wouldn't grow as much, right? If sunlight was limiting for them. Similarly, if periphyton was a limiting resource for the snails, then we might expect that snails might grow better at low snail density, for instance. All right, so what was going on? So looking at data for periphyton first. So I've just circled a couple here. So we've got photosynthetic rate on the x-axis, snail growth on the y. But just looking at the periphyton first of all, looking at the periphyton photosynthesis, we look at low snail density up at the top, and we find that, in fact, the periphyton are photosynthesizing more rapidly at the open site. So it looks like when there aren't a whole lot of snails around, the ability of the algae to photosynthesize is really affected by light, right? So essentially there's not enough light to go around. It's limiting photosynthesis when there aren't a whole lot of snails around. Interestingly enough, when there are snails around, it doesn't have that much of an effect. So look at the bottom, and those two circles overlap quite a bit. The open and shaded sites have basically, really close to the same photosynthetic rate. So it looks like when you don't have many snails around, resources become limiting. And if you're thinking of HSS fretwell here, good for you. Good for you. All right, well, what about the snails? So if you look on our y-axis now, we've got snail growth rate and snail lipids. If we're looking at both of these axes, both of these graphs here, we're seeing that in fact the snail growth rate is higher, and lipids are higher as well when there's low snail density. So essentially when snails are released from competition, when we reduce the amount, then they're able to grow faster and store more lipids. So it looks like in fact competition is playing a role under normal circumstances in limiting growth of the snails. So this is how you figure out if resources are limiting, right? You increase the per capita resource levels and you see if there's a change in growth. So in streams, competition can be important. Now, one thing that I wanted to mention, and this is, I'm recording this on Halloween, so perfect timing, right? The ghost of competition past, don't be scared. We might not observe species competing with one another. We might not observe them fighting with one another for resources, chasing each other away. We might not observe that. And it could be because they've already partitioned their niches. So what we might see is the outcome of competition in the past. So in times in the past when resources were scarce and competition was intense, that caused species to specialize resource-wise and to partition their niches. And so we don't see competition now. So the ghost of competition past is just this idea that communities now may not show the processes anymore that structured them in the past. So just to review then, to reduce competition, a couple things. Anything that increases resource levels or decreases the number of potential competitors. And so thinking about streams here, think disturbance, right? Disturbance can come through and reduce the number of potential competitors, right? It could be a drought, could be a flood. It moves individuals around, it kills some individuals. And so because streams are dynamic and subject to disturbance, this can play a role in reducing species competition.